Okay, part 3 of chapter 12. We're actually going to skip the preparation of phenols. You are going to look at some different reactions with aromatic substances in organic 2, so I will leave that to our future selves. So you can skip 12.8. Skip 12.8. All right, now we've prepared alcohols. We've reviewed several of the ways that we've learned in the past. In the first part, we looked at the Grignard reaction, a really important reaction that results in an alcohol in part 2. And now in part 3, we are going to look at reactions of alcohols. All right, so now once we have alcohols, what are some things we can do with them? So first of all, there's a few review reactions here. So first, a few we already know. And for one, substitution. All right, you can take an alcohol and treat with a halo acid, a hydrohalo acid, and you can get a substitution. All right, and that can go through SN1 or SN2, just depending on your substrate. All right, you start off by protonating the OH in either mechanism. And then the second step, it just depends on if you're doing SN1, leaving group leaves, or SN2, where it's all concerted. But this is chapter 7 review. So we're not gonna hang around there for a long time. There are a few other reactions where we can replace an OH with a halogen. And I don't necessarily want you to know the mechanisms, but I want you to know the reagents. All right, so the zinc, there are a few. Okay, so here they are. We'll go back to that last slide, but these are the ones I wanted to show you. You should know SOCl2. This is called thionyl chloride or SOCl2. The PY is just pyridine. It's a base. It's there to pick up protons. This is the reagent that I really want you to focus on. That will convert alcohols, primary or secondary. I'm not going to try to trick you there, right? So we're going to have alcohols here with thionyl chloride will give you the alkyl chloride. And then one that's really nice for synthesis is very easy, PBr3. So that will take your OH and it will replace it with a bromine. I'm not asking you to know the mechanism of either of these, but I do want you to be able to predict the products or be able to use the reagents if you had to predict the reagents. Another way that we can replace, right, so we're still on substitution, you can make OH a better leaving group by using tosyl chloride. Don't forget that guy. And there's usually pyridine there as well. This doesn't make it an alkyl chloride. Remember, this is a little bit different. It's going to make it an OTS. Now it's just a good leaving group where now you could, if you wanted to make an alkyl halide, just another way, you could use NaCl, and that would put a chlorine there. You could also eliminate, right? So you could use a really strong base, and you could get a double bond. All right, so don't forget about this little reaction. This is really nice if you get stuck with an alcohol and you're not sure what to do with it. Make it an OTS, and then you can get rid of it or replace it really easily. Make sure I didn't skip anything. Yeah, so no new mechanisms right now. The SOCl2 mechanism is interesting, but you are not responsible for providing that mechanism on an exam. Same with PBr3. If it comes up in the homework, you can look it up. But on the exams, I will not ask you about it. The elimination, you can eliminate with OTS like I showed up here in this example. You can also eliminate with acid catalyzed dehydration. And in this case, you just want to use concentrated acid, right? And that will also give you the elimination reaction. Now, what's important to know is this will always give you Zaitsev. So if you do want a Hoffman product, you need to use the tosyl chloride and the bulky base. So you do have options for elimination. If it's a Zaitsev elimination, though, this H2SO4 certainly works. You have already done this mechanism, so we're going to keep going. Right, there's the elimination. The less substituted alkene will only be favored using the bulky base. Just reiterating what I said right here. Right? If you want to use a bulky base, you have to make it into a tosylate first. If you treat this guy with that bulky base, nothing is going to happen. It's just going to deprotonate. Right? Because OH is not a good enough leaving group by itself in this scenario. Right? So tosyl chloride. Then you can use... in this case, it doesn't matter which base they use, right? Because all of the directions are the same. This would give you the Zaitsev base, though. All right. Now, we talked about reduction as a way to make an alcohol. So now let's go in reverse. We're going to talk about oxidation of alcohols. 2 carbonyls, right? So when we made the alcohols, we were reducing the number of bonds to oxygen, going from a double bond to a single bond, right? Remember, we use sodium borohydride or lithium aluminum hydride. Now we're going to be increasing the number of bonds, right, from 1 to 2. In some cases, it'll be even to 3. So there are different oxidizing reagents. It's important to keep your reduction and oxidation reagents organized in your mind. There are something that we're going to call partial oxidation and a full oxidation, and it just depends on our starting materials. Right? A primary alcohol is going to have 2 hydrogens and an R group and an OH versus a secondary alcohol, which would have 2 R groups and an OH. Now, they both can be oxidized to give an additional bond to oxygen, H and R, right? With the secondary also giving us, I'm going to put the R groups like this, giving us a ketone. What's interesting, though, is when you start with a primary alcohol and you wind up with an aldehyde, this could be oxidized again to give us even more bonds to oxygen where that H is replaced. Right? And I'm going to flip it around here, and it would be a carboxylic acid. Right? So secondary alcohols will always give you ketones. Primary alcohols could give you aldehydes or carboxylic acids depending on what reagent you choose. So let's get into some actual reagents, right? And this is a no-go. Another thing they're going to point out here is tertiary alcohols, right? Where you have 3 R groups. They generally will not oxidize, so you'll get a no reaction here. There's one example of something that can oxidize a tertiary alcohol. No, you don't learn any of those in like the entirety of Organic 1 and 2. So for now, you just know that's a no reaction. What kind of reagents are we going to use? Now, for our full oxidation, so this is going to take us to the most bonds possible, we're going to use a chrome reagent. Now, there are a few different ways that we can get to this chrome. Now, I'm going to show you what I use most of the time is sodium dichromate. It needs some acid and water, but this is going to give you a full oxidation. This could also be written as chrome trioxide in water. Sorry. Oh, no, acid. I had that right. And acetone. Both of these do the exact same thing because in situ, what they make is chromic acid, H2CrO4. This is what is actually reacting. You just can't, it's not stable by itself. So you have to kind of make it in situ, either this way or this way. This is the one that I'm going to show most frequently. Chromic acid is also called Jones reagent, and you are more than welcome to just write Jones reagent. I couldn't for the life of me explain to you why I, Lindsay Jones, don't write Jones reagent, but it's just where we are in life. All right, this is the one you'll see from me. All three are appropriate and will do the same thing. So let's take a look at what they do. If we have a primary alcohol and we treat with sodium dichromate or chromic acid, chromium trioxide, or Jones reagent, we are going to make a carboxylic acid. Right, that's what we mean by full oxidation. We get as many bonds to oxygen as possible. If we're dealing with a secondary alcohol and we use Jones reagent, sodium dichromate, H2SO4, and water, we're still going to just stop at the ketone. We aren't going to break carbon-carbon bonds here. But what if we want to stop at the aldehyde, I'm sorry. And again, this is another example where you don't actually have to show the mechanism. You just need to learn the reactions. What if we want to stop right here? What if we don't want to go all the way to the carboxylic acid? Well, we have an option. The partial oxidation with something called PCC. Now, you only have to ever write PCC, but it stands for pyridinium chlorochromate. So it's still a chrome reagent. It's just not as strong, right? It's still going to oxidize. It's just not going to oxidize as far for a primary alcohol. If you use PCC with a primary alcohol, you will stop at the aldehyde. However, if you use PCC with a ketone, with a secondary alcohol, you're going to still get the ketone. So secondary alcohols, you can use whatever oxidizing agent you want here. With primary alcohols, it's going to make a big difference. Tertiary alcohols are not going to will not react with any of these. All right, so you can see secondary alcohol right here, no matter which direction we go. Full oxidation, partial oxidation, that's as much as it can oxidize. We are not going to cover the Swern oxidation, so you can skip that last little bit. There are lots of different ways that you can oxidize things. There are lots of different reagents for most of the reactions you learn this semester. And there might be reasons to use them for increasing yields, for protecting other parts of your molecule, expensive reagents. Oxidations, a lot of times it's toxicity. Chrome is pretty toxic, or chrome-6 reagents are pretty toxic. We're not going to cover Dess-Martin and Swern, but just know there's lots of different options. Just to do a little practice here, let's think about what would happen if we have our H2CrO4. So essentially, if we're taking this is Jones reagent or sodium dichromate or chrome trioxide. This is what it's making in situ. You're never going to see me type that, but that's what is actually doing the reacting. So if we take this, let's see, we have an aldehyde, we have an alcohol, we have an alcohol. And we're going to treat it with the full oxidizing reagent. Everything's going to oxidize here that can oxidize. So your aldehyde will become a carboxylic acid, right? It will keep oxidizing. This little wedge that was coming towards you, You don't have wedges and dashes on a trigonal planar carbon. That just becomes flat and you get a ketone. Then down here, nothing should change the stereochemistry on that carbon. We're not touching that carbon. It's this carbon out here that's going to be oxidized. And this is a primary alcohol, right? Because there are 2 hydrogens here. So this is going to become a carboxylic acid. All right, so watch for examples that have multiple groups. I love doing that. So if I want to test your knowledge of, say, PCC, let's maybe start over there. And I want to do something like this. You know, this is a pretty common way for me to test both primary and secondary. In fact, let's make it even better. We'll even have a tertiary alcohol in here. If I treat this with PCC, I'm going to stop at the aldehyde for the, let's actually stop at the aldehyde for the primary alcohol. I'm going to get a ketone for the secondary, and I'm not going to get any reaction on the tertiary. All right, this is going to apply to all of those alcohols on that problem. Right. Aldehyde to carboxylic acid, secondary to ketone, primary to carboxylic acid. We are not going to go through biological redox reactions. If you take biochem, you will get into that. And we're also going to skip oxidations of phenols. Now, I wanted to get through, if you're keeping track, you can skip 12:11 and 12:12. Okay. I am not going to go through all of the synthesis strategies here, but I encourage you, as I do at the end of most chapters, Klein loves to give you some references, some good ideas here of what you can do, some flow charts for, this is great for synthesis, especially when you have to ask that question, am I extending the carbon chain? If you're extending the carbon chain, right, you know that you now have Grignard. If you are changing functional groups from alcohols to carbonyls or vice versa, you have a bunch of options, right, through your oxidations and reductions. This is a great chart to help you study and to work with as you work through synthesis problems. You can think of it as, I've made you start at an alkane, and let's say I want you to make an alcohol product. Just on a functional group level, you know you have to go to an alkyl halide, and then from there you could go to the alcohol. If you were trying to go to a carbonyl, right, you can do the same thing. In fact, there are multiple routes that could get you there. Let's let them go. You could go this way, right? There's lots of options. And pay attention on synthesis problems. I often limit you. So if I tell you you can only use alcohol starting materials, but you want an alkyl halide, then you also have to be able to transform that. I think that's it for chapter 12. Again, please go through those synthesis strategy slides on your own. They're helpful. I will start posting chapter 13 towards the end of the week, and chapter 13 will be covered on the final. Thank you.